Hey everyone, and welcome to The Explainer. If you're a structural engineer, you know that the codes we rely on, well, they're basically the tools in our tool belt, right? They dictate exactly how we build, how we ensure safety, and really, how we push the boundaries of modern design. So today, we're going to open up a newly upgraded toolkit together, the ACI 31819 Concrete Code Updates. Now, transitioning from the older ACI 31814 to the newer 31819 code, it brought some massive, highly technical shifts to the way we calculate and visualize internal forces. It's a lot to take in. So in today's explainer, we're going to distill 3 of the most complex, highly technical updates from these standards into clear, accessible concepts that you can actually take and immediately apply. Here is our structural roadmap for today. First, designing with ACI 31819. Second, the strut and tie method. Third, mapping column strength. Fourth, new rules for shear. And fifth, building safer structures. Let's jump right in. Section 1. Designing with ACI 31819. Laying the groundwork. All right, so to start, we really need to look at the fundamental behavior of concrete members, and more importantly, why our standard linear assumptions sometimes just completely fail us. The absolutely crucial point here is understanding the difference between B regions and D regions. For the longest time, structural design has relied super heavily on Bernoulli's classical beam theory. You know, the whole idea that plane sections remain plane. And hey, that applies beautifully to what we call B regions, or beam regions, where the strain due to flexure varies linearly through the section. It's safe, it's predictable. But then, we have D regions, disturbed regions. These pop up near an abrupt change in geometry or loading. Think like a corbel or a really deep beam. And surprisingly, within a distance h from these discontinuities, the strain distribution becomes highly nonlinear. Standard linear math, it just completely falls apart here. We literally have to use a different approach.
Section 2. The strut and tie method, X-ray vision for concrete.
So when standard assumptions fail, we pull out our next tool. Now, what's really interesting about this slide is how this essentially gives us X-ray vision right into the solid concrete. What you're looking at here is a strut and tie model, or STM for short. Instead of looking at this solid, confusing block of nonlinear stress, we're simplifying the complex internal forces into a really clear, two-dimensional truss. See those dashed green lines? Those are our struts. They represent the flow of compressive stresses. And that solid red line running along the bottom, that's our tie, which is handling the tension. And notice how they all connect at specific pin-connected joints? We call those nodes. This entire model complies with the lower bound theorem of plasticity. Basically, that just means as long as this internal truss is in equilibrium and your components don't exceed their yield limits, the structure is absolutely going to safely resist the applied loads. Now, developing an STM under these ACI 31819 guidelines involves a very specific logical process. Step 1. You determine all your applied loads and reactions. Just map out exactly what the structure is holding up. Step 2. You pinpoint those D regions we talked about. Look for those areas near geometric or load discontinuities where the strain is going to go nonlinear. And finally, step 3. Calculate the forces transferred at the boundaries of those regions, and then design your struts, ties, and nodes to handle those exact loads. It's brilliant, really. It transforms these abstract, chaotic stress fields into a very solvable geometry problem.
Section 3. Mapping column strength. Deconstructing the envelope.
Okay, let's pivot from the internal trusses of deep beams to the true vertical workhorses of our structure's reinforced concrete columns. Here we've got a physical representation of a tied reinforced concrete column. It's your standard 16 by 16 inch cross-section. Now, if you look at the internal layout on the right side, you can see it's reinforced with 8 number 9 rebar bars, perfectly distributed. But here is the million-dollar question. How do we accurately predict exactly when and exactly how a column like this will fail when it's subjected to varying loads and bending moments? Well, we have to map its strength dynamically. And this brilliantly illustrates the solution. This is a 3D interaction diagram generated for that exact 16 by 16 column. Think of this wireframe shape as a definitive envelope of safety. Your vertical axis represents the axial load, so you have compression at the top, tension at the bottom. The horizontal axes, those represent your bending moments. The software is actually calculating exact control points for you, things like maximum compression, the exact points where the tension reinforcement yields, and pure bending. Here's the bottom line. If the combined force of your real-world load falls safely inside this blue bubble, your column is good to go. If it pokes outside that wireframe even a little bit, you have a failure. It's a highly visual, mathematically rigorous way to define the exact limits of your components. Section 4. New rules for shear. The shear shift in ACI 31819. Okay, let's dive into this because honestly, this is a massive shift from the previous code. We're opening the final and maybe most significant compartment of our toolkit here, the concrete shear contribution calculations, known as VC. Under the old ACI 318-14, engineers could use a pretty simplified equation for VC. Basically, as long as there wasn't an axial force present, the actual area of shear and flexural reinforcement wasn't really a major consideration in that simplified equation. But under ACI 318-19, everything changes. The calculation for VC is now entirely dependent on whether your provided shear reinforcement, your AV, is greater than or less than the minimum required shear reinforcement. If it's greater, the new code forces you to factor in both the axial load and the flexural reinforcement ratio just to find your concrete shear capacity. But what if your provided shear reinforcement is actually less than the minimum required? Well, ACI 31819 is addressing a really critical physical phenomenon here. I'm actually going to read this directly from the source material. Experimental tests have indicated that the shear strength of concrete does not increase in direct proportion with member depth in non-pre-stressed members with minimal shear reinforcement. I mean, just think about that for a second. As these members get deeper and seemingly beefier, their proportional shear strength actually drops. It's so counterintuitive, right? So because of this inherent weakness, ACI 31819 introduces a brand new variable. It's called lambda s, the size effect modification factor. Since deeper members lose proportional shear strength, this new factor legally forces engineers to mathematically account for that weakness right in their calculations. Section 5. Building safer structures, real-world applications. So let's bring all this theoretical math back to reality. All of these code changes and new models, they mean absolutely nothing if we don't know where they physically apply on the job site. These stringent new shear rules, especially having to use that size effect modification factor when your shear reinforcement is minimal, directly impact the design of several vital structural elements. You're absolutely going to be using these updated equations when you're designing deep beams, when you're calculating the capacities of one-way and two-way slabs, and when you are detailing out-of-plane shear reinforcement in large structural walls. It's basically a fundamental tightening of the mass to ensure greater safety across the board. Well, we've covered a lot of ground today. We explored the chaotic, nonlinear behavior of D regions, we visualized hidden stress fields using the strut and tie method, we mapped 3D safety envelopes with interaction diagrams, and we completely decoded those massive new shear rules in ACI 31819. So, I want to leave you with this final thought to chew on. How will these new dimensional limits, size effect factors, and internal stress models change your approach to your next major structural project? Are your designs fully utilizing this upgraded toolkit yet? Thank you so much for joining me for this explainer, and as always, keep building safe.